Hi, I'm Francesco Giuliari and I will present the work Spatial Commonsense Graph for Object Localization in Spatial. This work is a collaboration between the Italian Institute of Technology, the University of Genova, the University of Verona and the Bruno Kessler Foundation. In this work, we present a novel task of locating object in partial scene, which involves locating an object in the unseen part of the scene. So, given a partial 3D scan of a room and an object we are trying to locate, we want to predict its position that is somewhere in the unobserved part of the scene. To describe the scene, we use a graph representation that encodes two types of information. The first one is the object arrangement. So we start from the semantic annotated point cloud of the partial scene, we identify the objects that are inside the scene, and we treat them as nodes in our graph representation. Between these object nodes, we define a type of edge that we call proximity edge, that define a distance from one object to another. This can be small, for example, for the case of bed and pillow, or larger for the case of, for example, bed and counter. Because every object node is at a certain distance from another object, all these objects are connected in a fully connected manner from each other. The second type of information that we encode in our graph representation is the Commonsense knowledge. This is an information that we extract from an external knowledge base that is called ConceptNet and describe, for example, where objects are located and how objects are typically used. From this new information, we create new nodes that we call concept nodes, and we encode them in the graph and we connect them to object node with two new types of edges, the edge location edge and the used for edge. We call this new graph representation that describes the scene in this way Spatial Commonsense Graph because it allows us to do spatial and commons reasoning for the localization. Our method for the localization takes as input the Spatial Commonsense Graph. The node features in the Spatial Commonsense Graph are word embedding that describe either the class or the concept, and the edge features describe the edge type and the distance if the edge is of type proximity. For the localization, we insert a new node in the graph that we call target node that describes the object we are trying to locate, and we connect it to the other object nodes in the graph with the proximity, but the distance is set to unknown, which is what we want to predict. Our method for the localization is a two-stage approach that we call SCG object localizer. In the first stage is a graph convolution network that we call proximity prediction network. That first it updates the node feature via message passing with an attention mechanism, and in the second part it concatenates the updated feature for the target node and the updated feature for an object node, and with an MLP it predicts the distance from that target and from the target object and that particular object node. The second part of the method is called the localization mode. It takes as input the proximity prediction, the proximity distances predicted by the PPN, and it converts them as in spheres around each object in the visible part of the scene, and then with spherical intersection, it tries to find a point where all these spheres intersect, and that will be our final localization. Here we have kind of a graphical representation of the output of the two parts of the network. Here we can see a scene. The yellow part in the background is the visible part of the scene. The colored dots are the various objects that are in the visible part of the scene, and the blue circle are the predicted distances from an object to our target object, the one that we want to predict. Here is how the output of our localization module that takes as input the pairwise distances predicted at the PPN, and it gives an output, a likelihood estimation on the localization estimate. To evaluate our approach, we had to build a dataset of partial scene. So we started from a dataset of fully reconstructed scene that is called ScanNet, that provide a full reconstructed room for realistic indoor environments. And ScanNet also provides the RGBD sequence that was used to reconstruct the full scenes. We take sub-sequence of that sequence that was used for the full reconstruction, and we can get the partial reconstruction for that particular scene. And this is how we build the data set. For the evaluation, we evaluated our method against some statistical baseline as well as some previous state-of-the-art localization method that we adopted for this task, and we had 3 performance metrics. The first one is the mean MPPE, that stands for mean predicted proximity error, and this is the mean absolute error on the predicted pairwise distance. So on the distances predicted by our proximity prediction method. The second metric is MSLE, that stands for mean successful localization error, and is the mean absolute error on the final localization, but only on successful localization. And we consider our localization to be successful if our estimate is within 1 meter of the ground truth estimate, which is a common threshold that was used for a similar task. And finally, we have the LSR, that is the main metric that we use when comparing against different methods, and is the localization success rate, and is the percentage of successful localization across the dataset. And again, successful localization is when our predicted estimate is within 1 meter from the ground truth location. So we tested some statistical baseline first in order to understand the difficulty of the method, and then we started to compare with the previous state-of-the-art approaches like layout transformer. The layout transformer is a method based on the transformer architecture that was proposed for layout estimation, and we adopted it for audience localization. And with this method, we were able to achieve an LSR of 17.6%. Then we tested our method in different settings. So first we have the GNN without Commonsense. Here we use our proposed approach, but without any kind of Commonsense information. So we use the spatial Commonsense graph, but only with object node and only proximity edges. And here we are able to achieve a localization success rate of 21%. And finally, we have 2 variants of our full approach that use the spatial Commonsense graph in its entirety. We have first tried with the learner embedding, and then with the word embedding provided us from ConceptNet. And with those, we are able to achieve an LSR of 23.8%, that compared to the previous state-of-the-art approaches is 6% higher. In terms of ablation study, we first try to understand the effect that different types of relationship have on the localization success rate. We try first without any kind of common sense information, then we try with only the at location, then we only used for, and finally with both of them. And we find that the relationship that was most useful was the location, because it allows us to prioritize the exchange of information on objects that have a similar location. But by using both of them, we were able to achieve best performances. Then we evaluated the effect that different attention layers have on our network. We found that without any kind of attention or using GATT, GATT-V2 or Han, we are not able to achieve as high a result as we have when using the graph transform architecture, which is what we use. And this is mostly because GATT, GATT-V2 and Han, they do not use the edge features when calculating the attention weight, and so they are not able to correctly estimate the attention weight in our setting or on our proposed graph. Finally, we tested the effect that using different numbers of graph convolution layers have on our performances. We found that only doing message passing once is not enough, so we need at least 2. But if we start to go with 4 or more layers, the performance starts to degrade, which is actually in line with what the literature say about using these graph convolution layers in a stackable way. Here we have some qualitative results of our proposed approach. Again, here we have 3 scenes. The yellow part in the scene is the part that was visible. The colored dots are the object in the environment. The cyan diamond is our predicted location, and the red star is the ground truth location of the object. So, in the first case, the network is trying to locate a bag inside a bedroom. It sees some bed as well as some nightstand, and the bag is placed at the foot of the bed on the other side of the room. And in this case, we can see that our network was able to correctly locate the bag. In the second case, we are in an office environment where we only see some desk and a sofa, and we are trying to locate another sofa. In the room, the other sofa is located on the other side of the room, opposite to the visible sofa. And again, here we can see that the network was able to correctly infer the correct position. And finally, we have a failure case, but it's a very interesting failure case because this scene is a conference room that is symmetric. So the network sees a table as well as some chairs that are on the table, and it predicted that the television should be behind the chair, on the wall behind the chair, at the head of the table. And in reality, the television was on the other side of the room, but it was still behind the chair of the opposite side of the table. So this is an error, but it's due to the symmetricity of the room more than the fact that the network was not able to correctly predict the location. So in summary, in this work, we propose a new task that is object localization in partial scene. We propose a dataset that we call partial scannet that has partial scene and can be used for this task or for a task that involves partial scenes. We propose a spatial graph structure that we call spatial commonsense graph that can be used for spatial and commonsense reasoning, as well as we propose a two-stage approach that can be used to do object localization in this partial environment, and it relied on the spatial commonsense graph that we introduced in this work. So thank you for watching, and if you have any further question, you can find me in the poster session. We can discuss them. Thank you.